video, we'll continue our look at Kepler's laws of planetary motion, specifically looking at his second and third law. However, for this video, we'll also introduce Sir Isaac Newton, because Sir Isaac Newton greatly expanded the understanding of what Kepler discovered. The two never met, never worked together, but more so on the part of Newton, because of Newton's work, it made Kepler's discoveries that much more important and feasible. So let's get started. So Kepler's second law states that when a planet is traveling around the sun, it travels faster when it's closer to the sun and slower when it's further. Something like this. If you watch what's happening here, it picks up speed when it gets closer and then it slows down when it's further away, right? That sounds great, but there's a problem, because if that's true, then the month of January would be shorter than the month of July. I don't know if that makes sense, but think about it. If we're traveling faster through space when we're closer to the sun in January, well, then when we're further away, time should be slower, right? But they're not. Basically, what Kepler's proposing would look like this, right? The time it takes to go through the month of January is faster than the time it takes to go through the month of July, all right? And that's part of the law that he discovered. So if you looked at the other months, how they laid out, it would be like this. So each time Earth completes the part of its revolution that's equivalent to a month, it's sweeping out an area of space in the shape of a triangle. All right? So what Kepler did was he measured the area of those triangles, right? 1/2 base times height. We could do that. We're not going to, but you could do that, and discover that if the planet revolves in an ellipse, which he said in his first law, it's going to cover the same area of space each month. I know that sounds very confusing, but this is what he means. So if the Earth moves from position A to position B, all right, the time difference, let's say is 30 days, is going to be equivalent to when the Earth is now over here in its orbit and it moves from here to here, all right? It's a shorter distance, but it's going to require the same amount of time because we're further away and traveling slower. I'm making a little bit more sense, I hope. So just watch this, all right? Same animation from before. Those colored circles, those colored triangles, while they don't look like they're the same, if I measured their area, 1/2 base times height, their area is exactly the same. So just remember that the time spent in revolution around the sun can be broken up into 12 equally sized triangles. And the Earth covers this distance equally in 365 and a quarter days, even though it's moving faster in the months where it's closer to the sun and the months where it's further away. And that's really it. I know it's a difficult concept to understand, but the motion is equivalent throughout. All right, it's faster at one point, slower on the other, but it's accounted for in the amount of distance that it covers during that time. So luckily, Newton was able to add to this theory and make some sense of it. Let's hope. One of the things that Newton said was that gravity pulls the Earth towards the sun. It's a force of attraction. And that force holds the Earth in place as it moves in its orbit. And as the Earth gets closer to the sun, it's going to pull harder on the Earth. Right? Gravity is going to pull on the Earth harder, and that will give it that motion that makes it move faster. As opposed to when it's at its further position, it's going to move slower because the gravitational pull is a little bit weaker. So we talked about Newton's law of universal gravitation. We saw this formula before, and applied to the theory of planetary orbits. Basically, the greater the distance between two objects, the weaker the gravitational attraction. The closer the distance between two objects, the stronger the gravitational attraction. So in the sense of an orbit, this is the planet Mercury shown here. The planet Mercury has a very elliptical orbit, a very, very weird shape. Because it's so close to the sun has a very strong pull on it. So its orbit is directly changed because of that. There's one more law of planetary motion that Kepler stated, and it's a little math heavy, but let's just take a look at it. He stated that the length of time it takes a planet to orbit the sun, its orbital period, is proportional to the average distance from the sun. In other words, that the time it takes for a planet to orbit, right, the time of a revolution, time, is going to be directly related to how close it is on average to the sun. So we'll do a quick mathematical experiment, if you will, to show how that works. So I'm using the solar system data chart in our reference table, and I'm going to use Earth as my model, but I'm also going to use Mars. So let's take a look at Earth and Mars, and we're looking at the period of revolution, how long it takes to complete a year. So obviously 365 and 26 days versus 687 days for Mars. So Kepler stated that if he squared the time to revolve, that would be proportional, the same as the cube of the average distance to the sun. So let's take Earth, all right? Earth takes 365 and 26 days to revolve. We're going to call that a year. So we converted days to years. We need to do the same thing with Mars. So for Mars, it takes 687 days. If we want to convert that to years, we'd have to divide 687 by 365.26, and the number we get is 1.88. So Mars takes 1.88 years to make one trip, okay, around the sun. Let's now move on to the other piece of data, which is going to be the mean distance from the sun. Here it is in our data table. 149.6 million kilometers versus 227.9 million kilometers. That's the average distance to the sun. For the sake of using numbers that are reasonable, that distance to the sun, which is 149,600,000 kilometers, is converted into astronomical units. This is a shortcut that astronomers made because they didn't want to use scientific notation. I kid you not. So that value is really equal to 1 AU. AU stands for astronomical unit. If we did the same thing with Mars and we converted its distance to the sun on average into AU, we get a value of 1.52 AU. If you're not following along, don't worry, you don't have to do this math. I'm just trying to prove a point from what Kepler discovered. So here's our numbers so far. For the Earth, we calculated 1 year is T. R value is 1 AU. For Mars, T is 1.88 years. R is 1.52 AU. So this was Kepler's work. He said, all right, if I take those values and I square the time and I cube the the distance from the sun, all right, for the Earth, 1 squared divided by 1 cubed, well, that equals 1. That's easy. Let's try that for Mars. Mars has different numbers. 1.88 squared divided by 1.52 cubed winds up being 1.01. That's interesting. All right, even though it's not exactly the same, it's a pretty close number to what the Earth's value is. Turns out if we use that formula for any planet in our solar system, they all have the same value. All right, look at that last column where it says T squared R cubed. All right, that's what we just calculated, and it's very clear that every planet in our solar system, including Pluto, has a predictable and similar value, which demonstrates that there's a clear relationship, and this is what Kepler discovered, between the time it takes a planet to orbit its star, our sun, and the distance from that sun. So that's a fixed relationship, and it's proportional. Thanks, Kepler. So that does it for Kepler's two laws, and in total, his laws of planetary motion. Thanks for watching.